Welcome back, everyone. It's now time to shift focus from using random forest for classification to using random forest for a regression task. So we're going to explore a regression task that is predicting a continuous label with a random forest model. We're also going to take advantage of this dataset to compare random forest regression with a wide variety of other regression models, such as polynomial regression or even support vector regression. In order to do this, we're going to be working with some artificial data, which is modeling X-ray signal versus rock density. Let's get a quick idea of what situation this is actually modeling. So we're going to imagine that we are boring a new tunnel into some rock. And in order to do this, we're going to be using a large tunnel boring machine. And at the front of the machine is going to be the actual cutting shield. That is the actual part of the machine that is cutting into the rock. And boring machines can have different cutting shields depending on the rock density. So we're going to imagine that in our particular case, there may be a situation where we want to actually change out the cutting shield depending on what type of rock we're actually digging or boring into. So in order to do this, we can use X-ray signals to determine rock density. And based on the rebound signal strength in nanohertz, we can estimate a density in the rock in kilograms per meters cubed. Now, we have some experimental results based on lab tests on a variety of rock samples. So what we did is we went to a lab and then we tested a wide variety of rocks with different densities, and then we tested the rebound signal in nanohertz. So we got something that looks like this. So keep in mind that we have here a signal and the rebound that was sent out versus the density of the rock. And what we want to be able to do is, with this artificial data set, create a generalized model, which could then be used to accept a rebound signal and output an expected density. So basically what we want is a model on top of this data. That way, when we're outside of the lab and we're actually boring a new tunnel into this mountain, I could measure the nanohertz signal that is fed back and predict what density of rock we're about to be tunneling into, which may necessitate a change in that cutting shield at the front of the machine. So we have all these data points from the lab, and hopefully we can build a generalized model so that when we're out in the field, we can actually figure out what is the best cutting shield to use. And notice here the unique curvature. It almost looks like a sine wave. And that's going to be important because we want to figure out what models can work well with this sort of data and what models cannot work well with this sort of data. So this generalized model is going to allow us to go out in the field, take a rebound signal measurement, and then report back an expected rock density value. And for this particular lecture series, we're going to be comparing a variety of regression models against each other. So the models we're actually going to be exploring are a lot of the models we already talked about. We'll look at linear regression, polynomial regression, and then k-nearest neighbors regression, decision tree regression, and even things like support vector regression. We'll talk a little bit about boosted trees regression, although keep in mind, we'll have a much deeper discussion on boosting in the next section of the course. Then we'll finally take a look at random forest regression. The reason we take a look at all these models is due to the sinusoidal wave aspect of this particular data set. Some models can just not perform well, while other models perform extremely well. So it's nice that we can visualize the model right on top of this. Some things to keep in mind is, similar to our very first studies on linear regression, we simply need our model to predict an output for the expected range of the rebound signal. So essentially what we're going to do, instead of focusing too much on something like a train test split, instead we'll be creating prediction outputs for an expected signal range, 0 nanohertz to 100 nanohertz. And that way we're going to be able to easily visualize model output to compare to the regression outputs that the data points in the lab gave us. So just keep this in mind as you compare outputs. You'll notice some models are able to produce smooth curves versus some models having that step or jagged output. All right, let's get started. I'll see you in the next lecture where we go to a notebook and begin working with the data with a simple linear regression model.